This is Srikanth S, Assistant Professor of EEE Department. In this session, I'm going to discuss the synchronous impedance method to calculate the voltage regulation and problems on this. So first, let us discuss what is voltage regulation. Voltage regulation is nothing but it is the difference between the no load voltage to the full load voltage. When the load is applied on the generator, what is the change which is occurred on the voltage? That is nothing but the voltage regulation. So voltage regulation of an alternator by EMF method involves the EMF quantities of all the armature parameters, such as which is all the voltage or depends on the armature parameters, where the armature parameters are armature resistance, armature reactance, and armature reaction. And this total drop due to armature reaction is not considered because the armature reaction value is less in the stator connected armature winding. So, because it does not occur due to any of the physical element but due to interaction of armature flux with main flux. So, because of this value is less in the armature reaction, whatever the voltage drop which is reducing is very less. So, that value we are neglecting. In order to quantify the voltage drop due to armature reaction, the armature winding is assumed to have a fictitious reactance called armature reaction reactance, that is X ohms per phase. Now the sum of armature leakage reactance and armature reaction reactance is called the synchronous reactance of an alternator. Here, because of the armature reaction, whatever the voltage which is reducing, for that we are considering one reactance X X ohms per phase. So this reactance is added to the synchronous armature leakage reactance. So these two will be called as, the combination of these two is called as synchronous reactance of an alternator, that is denoted by XS. And in order to get this XS value, we are going to do some tests on the synchronous generator. The two tests we have to do, one is open circuit test and one is short circuit test. Whereas in open circuit test, we are going to apply the rated voltage and we are going to take the parameters corresponding to the requirement, what are the no load voltage and what is the no load current. And in the same way, we have to go with the short circuit current test. In this short circuit current test, we have to calculate what is the full load current and full load voltage. Based on that, we have to calculate the synchronous reactance. So this is the open circuit test. As we know, the armature winding is connected to the stator. Armature winding is connected to the stator and field winding is connected to the rotor. So here the field winding is connected to the rotor. Rotor is having only one coil. So that is represented with a coil. And here the supply to the rotor or field winding is given by externally by using the DC supply, and this DC supply is also a variable DC we are taking in order to change the voltage values, because when the field flux changes, based on that no load voltage changes. So here we are keeping a variable rheostat which will gives us the different voltages from 0 to maximum. And here this is connected to the ammeter, and through ammeter which is connected to the field winding. And here whatever the three phase star connected alternator which is connected to the open circuited voltages, that is voltmeters which are connected to the line to line, which will gives the open circuit line to line voltage. And here we are going to vary the field current. We are going to vary the field current such that where this voltage varies, when the field flux varies, we are going to get the change in the voltage. So step by step we are going to vary like 0.1 amperes, 0.2 amperes, so on up to 1 ampere we are going to apply, and this voltage will read a line to line voltage until this voltage reaches the rated voltage. Until this voltage reaches the rated voltage, we are going to vary the field current. We are going to vary the field current. And once it reaches the rated voltage, we are going to stop the experiment. That is, we are going to minimize the field current, and we have to switch off the supply. So here we got the field current values and voltage values, line to line voltage values. And now we have to draw the graph between the field current versus load voltage or line to line voltage. Here the generator side is open circuited, no load is connected, so we can also call it as no load test. Here in the open circuit test, for determining synchronous impedance, the alternator is running at synchronous speed. And the main important thing, the alternator, whatever the input, mechanical input we are giving to the alternator, should run at synchronous speed. And the load terminals are kept open. This means that the loads are disconnected and the field current is set to 0. Here the loads are disconnected and the field current which is set to 0. After setting the field current 0, the field current is gradually increased step by step. Once the field current is increased step by step, the terminal voltage is measured at each step. At each step of increased field current, we are going to note down the terminal voltage which is measured at each step. The excitation current may be increased to get 25% more than rated voltage. Excitation current may be increased in order to get 25% more than the rated voltage. Not only the rated voltage, we are going to increase the excitation such that where the generator voltage reaches 125% of the rated voltage. Now a graph is drawn between open circuit phase voltage, that is ET by root 3, and field current. So the curve obtained is called open circuit characteristics. The shape is the same as the normal magnetization curve the linear portion of the open circuit characteristics is extended to form an air gap line. So here the linear portion of open circuit characteristic is extended to form an air gap line. Here this is the open circuit characteristics, this is the air gap line, and this is the open circuit characteristics, where here after reaching the rated voltage, the voltage is going to be nearly constant. It is under saturation. It is under saturation. What is saturation? Just for any magnet, if we consider, even though you increase the flux, its properties will never change. The magnetic flux density will never change because it has reached the maximum value of flux. So, sorry, maximum value of flux density. So, at that condition, even though there is a increase in the flux, there is no increase in the voltage. So, that is called a saturation effect. That is, it reaches a maximum value. And here we are going to take the open circuit voltage on the y-axis and field current on the x-axis. And this is the air gap line we are going to get. We are going to draw for the open circuit characteristics. Now we will go with the short circuit test. In the short circuit test, we are going to make the secondary side, that is whatever the stator windings are going to be short circuited. Short circuit is nothing but it is complete load is applied on the stator. Complete load is applied on the stator. And here we are going to place the ammeters in order to measure the current in the armature windings. Here when we change the field current, the short circuit current is going to change. So here, in order to get the rated current, short circuit is nothing but rated current. We have to apply full load values. That is nothing but we have to apply a rated field current which has to generate rated short circuit current, which has to generate the rated short circuit current. This rated value is given by the manufacturer for any generator. On the nameplate details, we can find the what is the rated current of the alternator. So here, when the field current increases, when field current increases, this short circuit current increases, because here this short circuit current, here ammeters are going to measure the current in the winding. When the field current increases, the short circuit current increases. We have to change the field current value and we have to keep the value at constant once the short circuit current reaches the rated value. Once the short circuit current reaches the rated value. Once the short circuit current reaches the rated value, we have to note down what is the short circuit current and what is the field current. And here the field current should be decreased to 0 before starting the alternator. In every step, we have to make the field current should be 0 before starting, and each ammeter should have a range greater than the rated full load value. Every ammeter is going to have a range that is greater than the rated full load value, and the alternator is run at synchronous speed, the same as in an open circuit test. The field current is increased gradually in steps and the armature current is measured at each step. And field current is increased to get armature currents up to 150% of rated value. Here, not only the rated value, we can take the values up to 150% of the rated value. Now, the value of field current and the average of 3 ammeter readings at each step is taken. A graph is plotted between the armature current and the field current. A graph is plotted by taking the armature current values and the field current values. Now, this is the short circuit characteristics. Here, when we take the armature current on the y-axis and field current on the x-axis, we are going to get the points such that where we are going to get a straight line which is passing through the origin, which is going to possess the linearity characteristics, and this is called the short circuit characteristics. This is called the short circuit characteristics of an alternator. Now we need to calculate the synchronous impedance. From the synchronous impedance, we are going to calculate the voltage regulation. The following steps are given below for the calculation of the synchronous impedance. First, we have to draw the open circuit characteristics and short circuit characteristics are drawn on the same curve and determine the value of short circuit current and gives the rated alternator voltage per phase. And the synchronous impedance will then be equal to the open circuit voltage divided by the short circuit current at that field current, which gives the rated EMF per phase. Here, what is synchronous impedance is? Synchronous impedance is the open circuit voltage divided by short circuit current. Open circuit voltage by short circuit current, at which the field current gives the rated EMF per phase, where at whatever the condition where we are going to get the rated EMF per phase. Here is the ZS formula. ZS is equals to open circuit voltage per phase by short circuit armature current for the same value of field current, where we are going to get the rated voltage, where we are going to get rated voltage. And synchronous reactance is determined as Xs is equals to square root of Zs square plus Ra square. Generally, Zs is equals to Ra plus Jxs. Here, Zs can be written as Zs is equals to square root of Ra square plus Xs square. So, from this equation, we can get Xs is equals to square root of Zs square minus Ra square. So, this is the synchronous reactance equation. Now, after getting the synchronous reactance, we have to calculate the voltage regulation. And how to take the synchronous reactance at a same field current where we are going to get the rated voltage. That is, here this is the open circuit voltage we are drawing, and this is the short circuit current, and here is the field current we are taking. and this is the short circuit characteristics we are going to get, and this is the open circuit characteristics we are going to get, and we are going to take at which what is the rated voltage. Here is the rated voltage point. At rated voltage point, at rated voltage point, what is the field current we have to take? So at this condition, what is the short circuit current we are going to get? That is nothing but rated current of the, sorry, short circuit current of the alternator. So here, in order to get the ZS AB by AC, that is here AB is the voltage divided by AC is the short circuit current. So here from the above figure, if we consider the field current IF as OA that produces alternator voltage per phase, the corresponding to this field current, the open circuit voltage is AB. So ZS is equals to AB in volts by AC in amperes. And here is the phasor diagram which we are going to calculate the no load voltage. Here is the V voltage, whatever the voltage which is generating with 5 phase angle difference between the current, and this value is nothing but V cos phi. And for any no load voltage is equals to whatever the rated voltage plus IA into RA plus IA into XS, or we can also take it as rated voltage plus IA into ZS. So this ZS is going to have the armature drop and the reactance drop. Here the armature drop is IA into RA, that is equal. This is the a straight line which is parallel to the current we are going to draw. And reactance component of current voltage, that is perpendicular to the armature current, that is I into XS, that is exactly 90 degrees displacement, and this resultant is nothing but the no load voltage. So here from this diagram, to get the OD value, OD square is equals to OB square plus BD square. OD square is equals to OB square plus BD square. Here E naught is equals to V cos phi, V cos phi and V sin phi. V cos phi plus IARA in whole square plus V sin phi plus IXS whole square. In general, E naught is given by E naught is equals to square root of V cos phi plus IRA whole square plus V sin phi plus or minus IXS whole square. Here, this is the no load voltage. And here where V phase is the rated phase voltage and IA is the phase value of current depending upon the load condition, and cos phi is the power factor of the load, and positive sign is for lagging power factor and negative sign is for leading power factor. So therefore the formula for percentage regulation is given as percentage regulation is equals to E naught minus V by V into 100. This is the percentage regulation of alternator equation. Now let us take the example. A 400 volts 35 kVA single phase alternator has an effective armature resistance of 0.3 ohms, an excitation current of 15 amperes, which produces 250 amperes armature current on short circuit, and an EMF of 380 volts on open circuit. Here, at an excitation current of 15 amperes, that is nothing but at a field current of 15 amperes, which produces 250 amperes armature current and 380 volts on open circuit. Calculate the synchronous impedance and synchronous reactance of the alternator. So synchronous impedance of the given alternator is Zs is equals to open circuit voltage by short circuit current. So 380 by 250 amperes, which is equals to 1.52 ohms, which is equals to 1.52 ohms, where Xs is equals to square root of Zs square minus Ra square, which is equals to 1.52 square minus 0.3 wholes 0.3 square, which will gives us 1.49 ohms. So we got synchronous impedance and synchronous reactance. Now we'll go with the another problem. At 25 kVA, 400 volts delta connected three-phase cylindrical synchronous generator requires a field current of 5 amperes to maintain the rated armature current under short circuit condition. For the same field current, the open circuit voltage is 360 volts. By neglecting armature resistance and magnetic saturation, its voltage regulation when the generator delivers the rated voltage at 0.8 power factor leading and at rated terminal voltage is. So here is the given data is 25 kVA, 400 volts delta connection. Open circuit voltage is given as 360 volts. Short circuit rated is equals to rated current, where IF is equals to 5 amperes. What is the rated current? We can calculate IL is equals to 25 kVA, 25 into 10 cube by root 3 into 400, that is equals to 36.084, 36.084, where I phase is equals to 36.084 divided by root 3, that is equals to 20.833 amperes, where ISC is equals to I rated field current is equals to 5 amperes, where XS is equals to ZS is equals to 360 by 20.833, which is equals to 17.28 ohms, where E is equals to square root of V cos phi plus IARA whole square plus V sin phi minus IAXS whole square. Here which is equals to, if we substitute these values, 400 into 0.8 plus 0 whole square plus 400 into 0.6 minus 20.833 into 17.28 whole square, which is equals to E phase is equals to 341.758 volts, where percentage regulation is equals to 341.758 minus 400 divided by 400. Here we are going to get percentage regulation as minus 14.6%. So here the voltage regulation what we got is negative. So in this session we learned about the synchronous impedance method. In that, what are the tests to be conducted and how to calculate the synchronous impedance method and some problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.